Hello. Hello, everybody. I would like to welcome the nicest cloud community here in Germany, and for sure the biggest one in Berlin. Thank you very much for coming. Thanks a lot for making this happen. I'll make it very, very short today because we have a lot of knowledge to share with you. So first speaker is Lennart Buttering. So Lennart is a very interesting person. I did some small research. He was born in Guatemala, right? Then he lived for several years in Brazil until age of 14.
Something like that. Yeah.
And then he moved to Hamburg. But this is not so interesting. The more interesting thing, intriguing thing, was for me that he started with Linux in 1995 with Slackware. Is that correct? So he wasn't fully convinced, but after 21 years, he came back to revolutionize the whole Linux stage. So, as you know, he created systemd, which is in almost any Linux distribution, and we are very happy to have it like that because it's amazing software. So please give him a big applause. For achieving this great thing. He has also many other cool stuff on his account, but he's here today to share with you knowledge about systemd. So this will be the first talk. The second talk is done by Sergiusz and Casey. They are both from the CoreOS team here in Berlin, so they have an amazing talk about Kubernetes, and they will show us how to set up a Kubernetes cluster running Rocket. Rocket, probably as you know, it's a containerization technology. We had few presentations in this meetup previously, and yeah, cool other news is that we are streaming this event. So thanks a lot to Factory Berlin to make this happen. We will see how it works. This is the first time, so I hope it will work out. But if not, we will improve definitely. Then another good news is we found resources to put all the recordings together. As you know, this is the third meetup for which we are recording, but we are not. Our YouTube account is not up to date. This will change. This will change definitely after this meetup. And the first and the last news is that we have two conference tickets to give away. So stay tuned. There was already a nice guy walking around giving you some numbers. But if you don't have a number, please reach to Chris. Chris, could you raise your hand? This is the organizer. And by the way, this is the nice guy from Kinvolk who organized the tickets. So also, Chris, thank you very much. And yeah. Yeah, we have also some CoreOS t-shirts, stickers, so stay tuned. Like today is the day. Okay. But t-shirts are there, so like an event full of gifts and presents, and yeah, I said it will be short. I'm stopping now. Lennart, the stage is yours.
Okay. Wow, that's loud. Thank you for having me. Of course, I'd like to thank DigitalOcean for having me here. I think at least officially I only got like 30 minutes. That's of course not the longest time. So it's probably going to stay a little bit superficial. Normally I do take questions during my talks because I much prefer it if we can turn this into something interactive than just me talking. Given that 30 minutes, that might be difficult, but if you have some really important questions, please do feel like you're invited to interrupt me. Yeah, this is supposed to be an introductory talk, so I'm going to give a superficial overview of what systemd actually is. And Then to actually give you a little bit of a feel how you interact with it, we'll then focus a little bit on one example how to use it. But it's necessarily going to be very superficial given that it's only 30 minutes. So let's jump right in. Systemd. What's that again? It's a system and service manager. That's how we call it. So service manager means it runs services. That's its primary focus. And a system manager is that it brings up the system, like it boots it up, keeps everything together, makes sure that everything stays running, and at the end shuts down the system again. That's like the shortest summary. Of course, in real life, it's a little bit more than that. Some people say it's a little bit too much. I tend to disagree, but it nowadays contains a number of different components. Where is it used today? Pretty much everywhere. So regardless of what distribution you use, any of the big public like community or company distributions, they all have it, at least in the more recent versions. So that's Debian, Ubuntu, Fedora, RHEL, CentOS, SUSE. If you run a current Linux, you most likely have come into contact with it. So what can it do for you? I mentioned that already. It's a service manager, so it manages services. It also does resource management. What does that mean? It basically means that for the service that you run, like one service being Apache, for example, or another service being MySQL, it can do resource management, basically saying, yeah, whatever happens, Apache gets half the CPU, and MySQL gets the other half of CPU. And similar rules, like you can apply them for any kind of resource there is, regardless if it's memory or CPU or block I/O or anything like that. It can also do logging, right? The reason it does that is because we consider logging a core facet of service management, because a service manager should be able to figure out when a service is not doing well, like if it fails, if it crashes or something like that. And if it does so, and you want to figure out why, then the logs are, of course, where you have to look. So we integrated that so that the service manager automatically collects all logs for the services that it runs, so that it can associate the service runtime, the service runtime state, with the logs generated from that service. It does device management. So basically, if you plug something in, if you pull something out, that something can happen, like that services are run. For example, like a network device shows up that something is started that actually manages that network device and similar things. It does login management. It's probably not too much interesting for the cloud crowd, I guess, but it is very much interesting for desktops and embedded devices that have any kind of user interface. It does network management. So, by the way, many of these things that I'm listing here are not something where systemd actually forces you to use that. It just makes you the office to do that. So, for example, network management, while it does contain a component, in many setups people will not actually use that because, like for example, on the desktop you would never use the network, like network D is the component systemd that does it, because we don't cover Wi-Fi, for example. We're mostly focusing on embedded and servers. It also does container management, a very limited way. If you want something fancier, use Rocket. And quite a number of things more, but we want to keep this superficial, so this is just kind of a rough overview of the areas it covers. How do you interface with all these components? The primary command that you should really know about is system control. System control basically allows you to interact with systemd start services, stop services, get the status of services, reboot the machine, anything, put it in a maintenance mode. It has quite a few of different commands. Some of them you probably come in contact with in your day-to-day administration work if you do that. Yeah, it's the most important command. Then there's another command. That's journal control. Journal control, like we saw on this earlier slide here, that the first thing was service management, the command to interface was that a system control. Then the next thing, like is logging. Journal control is a command to do logging, like to actually get the logs out. It's basically, if you invoke journal control, it's pretty much equivalent to doing a cut var log messages on traditional Linux systems, or depending on the Linux system, it might be cut var log syslog, whatever you have there. Journal control is pretty much like that. actually gets you the exact same like bitwise output, but it has quite a few bells and whistles. Like for example, allows you to search something by service and by whatever else, like PIDs and by user and things like that. So it's actually fully indexed in contrast to the classic log files that syslog maintains. The journal, which is the logging component of systemd, probably is enough of a topic to cover like 3 hours of talks, and you probably still would only know half of how awesome it actually is. So yeah, I'll just keep this brief here. System control, like the first command I mentioned up there, actually has a minimal log viewer as well, based on the same code, which is, it will just show you the 10 last log lines, for example. If you want to know some information about a service, it will show those to you. There's login control. Basically, all the tools that systemd provides that administrators interface with are always something word control. So you have system control, journal control, login control, and a couple of others. Login control allows you to see who's logged in. Again, probably not too interesting for the cloud crowd, but it is definitely interesting for desktop people. There's machine control. Machine control is something that allows you to enumerate and interact with local containers and local VMs. It's a little bit of an abstract interface, so it actually works with any container manager that wants to be compatible with it. Meaning, yeah, so basically LXC, libvirt LXC, and they're all called interface with that. And machine control gives you generic commands to get a shell, to copy files into a container or not. It also does work with Docker, at least in some distributions. But I'm not that much of a Docker guy myself, so I don't really follow the progress there. It's actually a neat little tool. There are quite a set of other, let's say, secondary commands that are a little bit more low level, that are not the primary interface, but more a secondary interface to systemd. I put some of them here on this slide, just to give you an idea what there is. Like, for example, systemd run is an extremely useful program. It allows you to run any command line you like as a system service in the background, right? So it's pretty much, if you have a command line that you can invoke in the shell, right, like for example echo foo, you can prefix it with systemd run. And if you do, instead of actually being spawned from the shell that you invoked it off, it will be run as a system service in the background. Why is that interesting? It's mostly because of resource management. Because any service that systemd maintains for you, you have resource management, automatic resource management, and explicit resource management by you from it. You also get logging automatically because everything that it writes will be, like writes to stdr, like to standard output or standard error output, will end up in the journal. You get, like it will be in a defined execution environment in the background, and quite a few other things. You can also use the command actually remotely. So it's an extremely useful command. Like for example, something that I use quite often is because I need to test my stuff a lot, because I've developed systemd after all. I have quite a few containers because it's so much easier to develop your inner system if all you have to do is reboot individual containers to test them instead of always have to physically cycle your machine. So systemd run actually allows me to run something inside of a container, right? So I can specify systemd run, then I have a special switch, -m, and I can specify a local container name, and then this command runs inside of it instead of on the host. Systemd run is actually awesome because it also allows you to have a system service that you put together on the command line, but you can also get interactive in and output to it. So yeah, it's an awesome tool. Another tool is systemd nspawn that we provide. It's actually a minimal container manager, right? It's kind of similar to what Docker does or LXC does or what all these things do, but it's much simpler and easier to use. It feels a lot like a cheroot. Right, you know, I'm pretty sure if you have played around with Linux in the past years, in the past 10 years or something, 20 years, you came into contact with a cheroot command. A cheroot, for those who do not know, is basically where you have a directory tree that consists of a complete operating system, meaning it has /user, /bin, /lib, and all these kind of directories in it. And with cheroot, you can actually run your own little environment. And then get a shell inside of that and manipulate it. Many people of you probably know it in context with containers sometimes, but primarily as a way to rescue your system if you fucked up your Linux system. Systemd and spawn is a lot like that, but it's 1,000 times nicer because it's actually good enough. Because it's a full container manager that actually makes sure that the execution environment is set up in a nice way. It actually allows you to boot up any, almost all Linux distributions just like that. So the chroot generally does not do that because the chroot doesn't provide you like the execution context that an init system of its own, like the service manager of its own, could run. Systemd and spawn does that. Yeah, it does very much the same thing as Docker in many ways, except that it's a lot more bare bones. It's pretty powerful, but it's really more like a building block than a polished, finished product. It's actually what Rocket is using as a backend, right? Because they think they figured out, and properly so, that the actually low-level work of setting up a container environment and running something inside of it might not be something that the container orchestration system should actually care about. And they basically use Systemd and spawn, which is our low-level tool, which is nicely integrated into Systemd and tries to do a lot of things right while still being somewhat minimal implements. Yeah, so much about the tools that we provide. There are quite a few other tools. Like I could actually, can you actually see this? Like if you try Systemd dash, then you see quite a few of them. Yeah, I don't want to go too much into detail into every single one of them. Oh, right. Sure. Got it. Okay. So, most of you will probably come into contact with it for the reason of service management, right? Because, I mean, you run your systems, and given that you're cloud guys, you usually run your systems not because you want to directly interface with them, but mostly because you want to run services somewhere on the internet. So the service management part of Systemd is probably the most important facet of it. To give you a very superficial conceptual understanding of what Systemd does there, let's say it basically implements a dependency network of a concept called units. A unit is basically something that needs to be viable during runtime or at boot for a moment. There are a couple of types of units. The most important type of unit is a service. And a service is exactly what you think it is. It's a process or a group of processes that get started and eventually get shut down. Example is MySQL as mentioned, or Apache or Nginx or whatever else you run. There are a couple of other units that also have like this concept that they have to be scheduled during boot, like they have to be started at the right time during boot, stay around for a while or until shut down, and then eventually are shut down. Those are socket units. I don't want to go into too much detail about those. Let's just say it's about doing on-demand activation of services, which allows you to increase the density of your service so that you don't have to run Apache all the time, but only on request when some client actually talks to it. This is actually really useful technology because, like, okay, I guess I'm talking about that anyway, even though I didn't want to. But it's actually really awesome technology, especially if you do cloud stuff, because it allows you to reach density if you have a very uneven usage profile of what you have to provide with. Like, for example, I know of one setup in the US where they have a one-click thingy where you can go to the website, do one click, and then you get your own private website, right? So that people can test it and then eventually can if they like it, actually pay for it and then keep it, right? So for those websites, it's like 99.9% of all the websites created that way are basically run 2 times, 3 times because people wanted to try it out. Only like less than 1% actually stay around and become payable customers, right? So for that case, the socket activation stuff, like the socket concept like the socket unit concept that we implement in Systemd is actually extremely useful because it basically allows you to run like 1 million services without actually running them, but only running them as soon as a network request comes in for them, right? So you basically tell Systemd, instead of run this service now, you just say, please listen on port 80 or port whatever you like. And when a connection comes in, then you start Apache. And Apache eventually quits and opens up the resources again. And then the next time something requests port 80 again, you get it started. So it's about density. There are a couple of other unit types. There's targets, which allows you to group services together. Like, for example, because if you, let's say you have for one customer, you always run one Apache and one MySQL, you can group them together. And then with a target unit, you can start them together and stop them together and introspect them together. There is a device unit. A device basically does what the name suggests. It's basically a way, much like a service is started at boot and goes away at shutdown or somewhere in the middle, a device appears at boot and is unplugged at shutdown, right? Why is this concept in systemd? It's mostly about scheduling the boot up correctly, right? Because if you think about it, if the system boots up, right, what needs to happen? First, the kernel initializes, passes control to systemd, and then it needs to collect a couple of devices, like, for example, hard disks, like, for example, the main root disk. Then it needs to run file system checker on it, which is a service. Then after that's completed, you need to actually mount it. So first, the device needs to show up. Then you need to run one service on it, and finally need to mount it. In systemd, these three concepts are basically all exposed under this unit concept via the type device and mount and service, right? So yeah, that way I already kind of explained what a mount unit is. Then there's an auto-mount unit, which is kind of what sockets do for services. Auto-mount units do for mounts, which basically means you can establish a mount without actually providing the backing file system to it. This is actually super useful in the cloud environment, because it actually allows you it's kind of if you have a service, right, and use the socket activation stuff to reach this huge density, and then a connection comes in and you start that service, then you might also want to just mount the backing cluster file system, whatever you have there, when the first write access or read access to that file system is done, allowing you to not only pack the services more densely, but also pack the file systems that are mounted more densely. Then there's swaps, there's timers, which basically allows you to run services based on time. There's pass, which allows you to run services based on the existence of a file or a directory being changed. There are slices, which is a concept, like a unit type for grouping a couple of services together for the purpose of resource management. This is, for example, interesting if you have for one customer 20 services and you want to group those just for the purpose of resource management as one, so that you basically can say, yeah, that customer at most gets this much CPU time, regardless what happens, even if the CPU is idle, and you can put them together in a slice. In many ways, it's similar to a target that I mentioned already earlier, but this one, like a target, allows you to group things for runtime purposes, the slice for resource management. And then there's finally the scope unit. A scope unit basically is a lot like a service, meaning that it actually it groups a couple of processes together and gives a runtime to them and collects logs, blah, 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 blah. The only difference towards a service is that a service unit is when systemd, like the init system, the system manager, starts the processes, and scopes is when somebody else does that and just asks systemd to create a scope out of it. Yeah, I went a little bit too much in detail about these different types. The most important thing to understand is that systemd manages more than just services. It's really about having dependency between services and other services, as well as services between to devices, services to mount points, and any other way. So, yeah, that's probably already way too complex, I figure. What you should understand is that in systemd, these units are named in a very uniform way. It's always some name dot that type. As one example, if you have nginx and it's running as a systemd service, it's called nginx.service. Nginx is the name of it, and .service is the type of it. It's like the most common type, again, the service. So, now this much about the theory, like the conceptual theory, very superficial view on this conceptual theory behind it. If you now actually want to interface with it, here are a couple of commands. I already mentioned system control is the primary command to interface with systemd. If you type system control and then some verb, and then some argument, something happens. In this case, start means start that service. It's pretty obvious. And then nginx.service means start that unit. Because systemd implements that dependency tree. If you run that, it might not just be that nginx's service is started, but some other kind of dependencies that have been declared somewhere else, and I don't want to go into detail too much how that's done. It's usually done by the packagers, not by the administrators. Yeah, so if you run that, then nginx will be started. One important thing, you can also write system calls throw start nginx without the suffix. That makes it a lot easier for administrators because, yeah, it's the most common unit type, and hence if systemd notices that you did not put a suffix to the unit name, it will just assume you meant service. So to make your life easier, it will do this kind of automatic extension there if there is no extension specified. There are quite a few other commands, like for example, system control stop nginx.service, which does exactly what you think it does. It stops the service again. There's system control status, which gives you information about the service, like how it's running, like what's the PID are. It's one of the most interesting commands. We'll actually come to an example for that later. There's system control restart, which does exactly what you would guess it does. It actually stops the service and then starts it again. There are quite a few other commands. Just as one example, here's one of the more complex kind. It is called system control set property. Set property is the verb how you can ask systemd to change some parameter of a service or of any kind of unit during runtime, instantly. In this case, we set a property on nginx.service, and that property is called CPU shares equals 500. Now, this is about resource management. It implements, basically, the way how the Linux kernel nowadays schedules services is via the CPU shares concept, where basically it says that every service gets by default CPU shares equals 1024, and then every service that deviates from that, right, that gets CPU shares 500, for example, gets only half the same amount of CPU, and if you set it to 2000, it gets double the amount of CPU, and you get the how that works. So with this command, we basically say run nginx.service, but give it a less CPU if the machine doesn't have enough than everything else, right? About half of what everything else gets. So this is just as one example. There are quite a few things you can invoke with set property. Actually, covering all of them would be way too much for this talk. And this is just one of them. Yeah, like you can set like all kinds of parameters with that. Like for example, you can say like this process should only get 3 gigabytes of memory. And if it gets more, it tries to get more, it will eventually get the OM killed and things like that. And this is like the last slide. Can you actually read that? I'm not sure if I can actually increase the font. I hope you can. This is just what I ran here is system control status. And it shows you basically the output of system control status. And there's a lot of interesting information in there. So, I mean, if you compare everything that I just talked about on the last slide with how traditional init systems worked, like most prominently System 5 init, which is probably what you have played with, like if you have been doing Linux already before. Much of it, like what I showed here on that slide, basically, at least for the top 4 commands, there are similar things. Like you can write etc init some service start to start something etc init. So it might look like this doesn't give you anything new, but system control status alone gives you a lot. So just to explain that, like for example, main PID, that line here, it shows you that line. It shows you the main process ID of the process, of the service. It shows you that there's a limit enforced on the number of tasks, which is 4915 tasks at Mac, but it currently only has 4. It shows you a C group. I don't really want to go into too much details about that, what that means. It's just about resource grouping. It shows you documentation. It shows you the actual state of it. Like the state is like the green thing. Do you see that? The green thing there, active, it basically says the service is active, right? If a service fails, right, if it crashes, aborts, or exits with some return error, then it will not say active there, but failed, and it would be red. It will also give you the time since when. So in this case, you see so that's 10 hours ago. So it basically has been running cleanly since 10 hours, and that's great. It shows you the commands that are running. It shows you quite a bit of other information. What it also shows you is like the last 10 log lines of that service, which is, I mentioned that earlier, that we actually consult the logs as well for system control. So compared to what System 5 had in that area, System 5, basically if you invoke the status command of System 5, all it would say is it's running or it's not running. This gives you a lot more information. And it can actually give you even more than this. So, how much time do I still have? 5 minutes. Okay, this is actually my last slide. We can now do questions for the last 5 minutes or something like that, or I can just play around with the command line to give you like more examples how it actually works. But let's first do questions. There's a question somewhere.
Test, yeah. I know that with the modifier -L you can actually extend the logging and you can have longer information. But is there any option to shorten the information? But because as you see here on the screenshot, actually the messages are all cut because all of the...
Oh, they actually aren't. Like, let me show that. If you like something that systemd does that we're doing, like Git did that, like the Git tool did that at first, and we adopted that as we do auto paging, meaning that if we notice that what we are outputting would be larger than the screen, we automatically invoke less. So you don't actually have to pipe to less yourself. You can still do that. It's actually smart. So it will notice that if the output is not to a terminal but to some file or some pipe command, then it will turn off the auto paging. But so just to give you the example, can you read that? I hope you can. So this is a command that I typed in to get the screenshot. Now we're running that the same way. And now you see, because my terminal is large, it will not do paging, right? You see everything. There's nothing truncated. Now we actually make the window smaller. Let's do that. So now, if I run that again, then it will not fit on screen. So it will automatically do the paging thing. So now I can actually go with the arrow keys up and down to actually see the rest of it, right?
Okay, thanks.
So we try to be nice to administrators. There are actually some people who do not like this behavior. I love it, and my opinion matters, so that's why you get it. Any other question at this point? Somebody must have a question. There's a question.
The set property, is it persistent again between reboots?
Yes, it is, if you wanted to. So basically, by default, is persistent. But you can also specify a -- runtime on the command line, and that will only apply to the current boot, and if you reboot, it will be flushed out. There's also a command called system control revert. It's at least in the most recent versions of systemd. I'm not sure, like some of the distributions like Debian are pretty old. They don't support that yet. But with system control revert, you can basically say, now reset everything to the original settings that the vendor supplied you with, right? So the idea is that with system control set property, you change something, you play around, you do your resource management, figure out how everything works, and make sure that all the resources are properly consumed, everything behaves nicely. And then if you made a mistake and say, oh my god, I'm not understanding anything anymore, you can just type system control revert nginx.service, and bam, it will throw away everything, all the changes you made, and will revert to the original versions that the vendor supplied. Systemd actually tracks very nicely the versions of the services that came from the vendor and the changes that you made. There are actually quite a few tools, not only the system control revert stuff that allows you to drop yours and revert to the original one. There's also systemd delta, which allows you to diff all your changes. So it's actually, I think it's much nicer to use than System 5 scripts traditionally used to be. Like, because first of all, System 5 scripts didn't allow you this kind of dynamic modifications during runtime. But secondly, there's no concept of distinguishing the vendor's original version from the version that you have locally on a system that you made changed.
So systemd revert removes changes in etc, leaving only user lib or whatever.
Yes, that's what it does. System control revert basically throws out everything in /run and /etc that you changed there, and reverts and it just keeps the stuff that's in userlib. Any other question at this time? That's the question.
Thanks for the talk. What is the benefit of configuring your network with systemd?
I think there's actually quite a few benefits of it. But so network D is that component of systemd that actually deals with network management. And network D works very different from, at least I think it works quite different from how the traditional network management solutions work, like which is on Fedora and CentOS on these operating system is the IF up-down stuff, and Debian has something similar, or network manager. So what we do actually is you write a file where you have a match section at the top. The match section at the top, basically, you can express with very simple settings. You can say, basically, apply this configuration that follows to all devices that match, for example, MAC address so-and-so. Or you can write all devices that match this name, and then you have a couple of, like, you can use wildcards. You can also say, match it to everything that is an Ethernet port. You can say, match it to everything, like quite a few different matches that about the device. So this enables you to write very generic configuration, because you basically can say with one file, you can configure the configuration for as many network devices as you have, right? Now you might think if you have a server, then there will only be one device. Right? But that's not really the case, or maybe there will be 10 and will never change. But that's usually not the case. Like as soon as you go into like virtualized environments and like especially in containers, then network devices can pop up and go like tunnels to other containers and these kind of things. And what networkd does is basically allows you to write one configuration file or 2 or 3 or something like that, a small number, and have them automatically applied to many of them. And then it can also do relationships between those, right? So it will not just do DHCP and these kind of things. It can also do something like you can express with one file, just one file, you can say whenever an Ethernet device appears, add it to this bridge, right? Or you can say whenever an Ethernet device appears that has an X as second character, add it to that bridge. Or and rules like that, right? And it's very, very simple to use. And then it also supports a lot of different like networking technology that the IF up-down scripts don't support, right? Like all kinds of gazillion weird tunnels that I don't even understand. And it has quite a few other things. Like for example, like the embedded people, like Intel is building that into routers. So for that, it has this uplink downlink logic, so that basically can say, yeah, my hardware has like 5 ports here and 5 ports there, and like this one is the uplink, and everything else is the downlink, and then it can say, yeah, now propagate the link beat from the uplink to the downlink and things like that. There's quite a few other things. It's much nicer, I would say, than the passive IF up-down scripts. And it's also a lot nicer, I like to think, than Network Manager, because Network Manager treats everything as a separate device, and you cannot write generic configuration for it, really. But do not be confused. networkd is nothing you would run on your desktop or on your laptop, because it doesn't do Wi-Fi. What it does cover is container, like execution inside of containers and on the host of containers. It's NVMs, like servers, and embedded devices. So that's quite a bit, I would say, but it's unfortunately, I like, yeah. It's also different is the way it works, like because Network Manager, if you run it, it takes possession of everything, right? networkd doesn't. networkd takes possession of everything where you have installed a file for that matches, right? And by default, it doesn't apply on anything, right? So there's a lot of other different, like for example, we really try hard to not be this project where we just stick weird things together that don't belong together and try to make one big thing out of it. We really try to solve that, like the problems properly. And that basically means networkd implements DHCP, for example, with its own little library, because instead of invoking the IC or whatever DHCP implementation that people tend to use. Now, some people say, oh my God, why do they have to re-implement that? We think it's the most trivial protocol in the world. Right? It's basically a protocol that says, hi, can you give me an IP address? And somebody responds, hey, do you want this IP address? And then you say, yes, I would like the IP address. And then the server says, there you have it, the IP address. So it's really that simple, right? And so we decided, let's do this properly. Let's not glue things together that don't belong together. Let's develop a single state engine for the network devices and turn it into something nice. Yeah, there are quite a few other things. It also has a minimal DHCP server implemented and things like that, which is really, really useful, for example, for cloud stuff, because you can actually do something like tell it to automatically pull a range of IP addresses for every network device that appears and serve DHCP on it. So it basically turns DHCP into something that you don't have to think as the concept of managing a service, but really as something that's just about managing a network device, and it's just that. It's just network technology, and if you're a server or a client, doesn't really matter. It's fully automatic. Like I mentioned, this nspawn container manager, this really minimal one. We actually ship a configuration file for that one by default, so that every instance of that little container manager that you run gets automatically configured a pipe from the container to the host, like a virtual Ethernet link, and then we automatically do DHCP server on the outer side and DHCP client on the inner side, and we automatically pick an IP range for that, and we automatically do propagation, and we do IP forwarding and things like that. And network D will also do IP forwarding, like tell the kernel to set that up. So I think there's a lot in it that makes it nice to use. But again, network D, we don't force you to use it, right? We couldn't, because we don't even implement Wi-Fi, right? But I'm pretty sure that people who actually look into it will like it a lot.
Yeah, sounds very interesting. Thank you.
It is.
Any other questions? Perfect. Don't be shy. This is your one life opportunity to ask the speaker here live.
Hi, my name is Alex. Question is, as I understood it correctly, journal enforces some sort of structure to the logs, right?
Yes.
Is there any kind of API facility or something similar where you could plug in structured log shipping to some aggregator, like Elasticsearch, for example?
The structure that we apply in the journal is very weak, right? We basically say what you're supposed to send us feels a little bit like an environment block, right? Like some variable name in uppercase equals some string, and then a couple of those. We collect that from the system. Like if somebody uses the classic syslog command, for example, that glibc provides, we set it on the other side. In that case, of course, the sender will not provide us with much context, so it will not be structured what we get, but we will add a lot of implicit context to it. Like, for example, what service is that on the other side? What user ID does it run? Which SLNox contact with PID? Which GID? Which audit ID? And quite a few implicit things. So even if you do not send us structured stuff, it will end up pretty much structured in the journal with a lot of metadata attached. You can get it out of the journal as well with an API that we provide. You can get it like with a C API. You can also use, let me show that to you. So journal control is the command that allows you to access logs. So I just ran that, and then we see, yeah, this is the first thing that I had logged. It feels a lot like, as mentioned, cat var log messages. If you do this command, journal control-o JSON, then you get the same data, but you will actually get it as a series of JSON blobs. So you can, if you want to, you can just process that if you don't want to use the C library. We also provide a very minimal a service, like a gateway service that opens pretty much that up to HTTP, right? It's disabled by default, but it's very trivial. It just really does the same stuff that I just did here, but opens up as an HTTP GET. And the journal is actually designed to make that nice. So if you are a web developer and you want to use that, you should actually be able to do that nicely, because we implicitly add something we call a cursor. Like, actually, that's what you see here. Like, just to show that, like, the lines are much longer here. But the first field that you see is this cursor thing, which basically identifies a specific log line, but not explicitly, but more fuzzily. And by fuzzy, I mean that usually log files are rotated, right? So if you pull some log files now and come back a week later, then hopefully you can just start off from where before. but very likely things got rotated away and you might miss something. So these cursors are fuzzy. So they basically say, yeah, if nothing got rotated away, then you will continue exactly where you left off. But if something got rotated away, it will put you to the next closest thing, right? Yeah, so your APIs are basically use a C library, use a journal control from the shell, or use this HTTP thingy. It's called systemd journal gateway D. It's completely up to you. And I know that there are libraries that also wrap the C API for other languages. I hope that answers your question. Yeah. Anything else?
I think I saw a question somewhere here.
No questions?
No questions?
Can you show, presentate, mount new features which was released few weeks ago?
Oh, the systemd mount?
Yes, please. Thank you.
How can I show that? Well, I have nothing to mount.
Just explain.
Does anyone have a USB stick I could mount? Something
Perfect.
that does not include porn.
A stick full of viruses.
So I talked about the systemd run thing, right? Now I hope this actually works. So I talked about the systemd run thing, right? Where instead of having a predefined service definition that comes packaged from the vendor, and then you install it in your system, then eventually you do system control start, and then that thing starts exactly in the definition that server applied. That the vendor wrote. Systemd run is more as a dynamic thing where you specify the command line on the command line and can specify additional parameters to it. So what systemd run is for services, systemd mount is for the mount units. I really hope you still follow in some way. So it basically allows you, it's in many ways a command that is equivalent to the classic Unix mount command, except in otherwise it's not. So the mount command, what it does really is it takes a block device or a network share and then mounts it and puts it somewhere in the file system. What systemd mount does is it optionally can pull in additional things. Like, for example, it will automatically pull in a file system checker, right? So that on the first access, you do not you actually get the file system checker run, which is like perfect for devices like these, because it's very difficult, at least to explain to my mother, that on Windows she actually has to unmount it cleanly if she wants the file system to not be dirty, right? So it's actually really, really handy, and I would argue it really should have been that way since 20 years on Linux, to run the file system checker automatically when you plug in the USB stick, right? Because the file systems are they are very likely to be broken file systems on it. Then something else you can do it. I already mentioned that systemd not only has this concept of mount units, but also this other concept of auto-mount units. Auto-mount units, as mentioned, are these things where you establish a mount point right now, but only actually back it with a real file system as it is accessed. This is also really, really useful for these USB sticks, because if you plug them in, right, then we can make it happen that the file system on it is not mounted immediately, but only the first time an application actually accesses to it. And we can also do the reverse, right? The moment that an application does not access it anymore, plus some timeout, we can automatically unmount it again. Which basically means that, yeah, if you actually care about USB sticks, which many people probably don't do anymore these days because we live in the cloud age, but still, if you still do care about them, then this is really, really, really nice, and how I would argue that USB sticks should always have been managed on Linux, right? So that we automatically do a file system check the first time they're accessed, that we only mount them as they are accessed, and that we unmount them automatically as quickly as possible when they're not accessed anymore, so that the likelihood that the file system stays clean is maximized, and the likelihood that the file system is fixed automatically when it's not clean is the highest. So let's actually try that. This demo might not work because I still have running UDEF, like this other component of Linux that will probably take possession of it first. Yeah, we'll probably see me failing. So that's udisks. Shit. So you just already mounted that. Let's undo that so that we can mount it with the mount tool with systemd mount. So if I invoke systemd mount now, I can do system mount list. And then what you see here is a table that actually shows the devices. Like all of that are basically my hard disk. And then the last one is a USB stick, like it shows. Like in the device path here, you see that's a USB device. And then we can actually mount it. Right, the first thing is a device node, and we just type SDB1. And then we do that as super user. Actually, we do not have to do that. And then it actually did that, and it basically created this mount unit, and it's mounted there. If you now look in the mount table, then we see that this is actually of type AutoFS, right? So it's not a real file system. And now if we actually access it, where's my mouse? See, at that moment, the file system checker ran in the background, and we mounted it. If we now quickly do this, that was not quickly enough. But now we did it right. You see that it's the AutoFS that is just there to make sure that when it accesses it gets mounted. And then you actually see the VFAT. Now if I type it again, it's unmounted again, and the file system is generally in a clean state. So is that your demo? It actually worked. Nice. Now, I demoed this with a USB stick. Because we live in the cloud age, USB sticks are not the hottest thing anymore. But the systemd mount tool is actually really useful even if you have network file systems, right? Like cluster file systems, NFS, whatever you like. Because with this, you can also dynamically create auto-mount points. You can just say, at that place, please put an auto-mount file system, and as it is first accessed, actually put something behind it. Yeah, it's a very useful, we can write a script basically that sets up an environment where some service is run only when it is accessed, and the file system that it's supposed to read its data from is only mounted at the moment it actually accesses and things like that. So you can write something where really only the initial hookups are done on the system, and the actual code and the actual file system mounts and all the expensive shit only comes when it's actually requested. Whose was that? I don't really see you, so I might not actually. Ooh, thank you for that. Should we do more questions if there are, or should we?
Yeah.
Like if there are there? There's nothing. I hope any one of you understood what I was saying.
Please wait. Let us record it for the streaming.
Okay, thanks. So you mentioned cloud volumes, right? Can you do an auto-mount point where the eventual device is, I don't know, let's say an EBS volume on AWS, and be able to identify what is going to be mounted there using AWS metadata, for example? Like, I only want to mount at this point this type of volume with this kind of tags on AWS or something similar like that.
So, I mean, what we provide is low-level tools, right? So we provide APIs. Like, for example, there's it's exposed via dbus, for example, how you can tell systemd to create an auto-mount point, or to create a mount pointer to run a service, or to run that, and things like that. We will only provide you some simple tools to make that user-friendly, like systemd run or systemd mount are some examples of that. But we will never be able to provide you with a full suite of things, right?
Yeah.
And the AWS support, like usually most of the more webby things that sit on top or are supposed to sit on top, we generally do not provide you with. But I'm pretty sure it would be easy to write something like that, right? Like, because we do provide you the APIs. Like, we see ourselves as the providers of APIs to the higher levels. Like, for example, for Rocket, we provide you the lower level engine for the container and the service management, resource management, things like that. We provide you, I would call, reasonably nice APIs for that. But what you want to build from it, it's completely up to you.
Yeah, actually, that's what I had in mind. The question was more like, can you be flexible there in filtering what kind of device gets mounted, like you do, for example, with network interfaces that you mentioned earlier, where you filter.
Well, I mean, it's a command line tool or a bus API.
Yeah.
It will do exactly what you ask it to do,
Okay.
right? So it doesn't do a matching or something like that. It doesn't do anything automatic. You can do that. Like, for example, for USB sticks, it's very easy because we have UDEF, you know, this device manager, and in its rules, you can basically say, run, like mount, pull in this auto mount, do it all automatically. But that's completely up to you. Like, there's a concept for that. But for network shares, that's a bit like, I mean, there's no concept generally with network shares about network shares appearing, right? Like, I mean, iSCSI doesn't do it, NFS doesn't do it. I mean, Samba, like SMB did, but who uses that? I don't know. So there's no concept of things popping up and things going away, really, for network shares. So if you want to mount something, you usually have to trigger it yourself and write a line first. And that's what systemd mount is. So it does not implement any matching logic on its own.
Perfect. Big applause.
Thank you very much. And I should not forget the most important thing, which is we actually have systemd.conf next week in Berlin. And that's why we are going to hand out, where's Chris, the tickets. Like, so the conference actually consists of 4 days. 1 day is for workshops, like, which is a full day of actually, like, where you can learn about systemd, various facilities. Then there are 2 days of talks and 1 more day of hacking, basically. Chris wants to hand out. You should probably come on stage. Okay. Okay. At the end, we'll give out 2 free tickets for the workshop day, but you can also pay if you want. Like, we still have some tickets left. We actually have some tickets left even for the main conference, right? For the main conference, for the other 2 days, we. Yeah, and you get food and stuff. Yeah, and of course the most important thing is there's going to be awesome talks about systemd from the guys who wrote systemd, from the community, and there's going to be people talking about the cloud and systemd, talking about embedded in systemd, talking about all kinds of things and systemd. So it was pretty nice last year, and I'm pretty sure it's even better this year. Yeah, so please consider coming, and yeah, next week at the Beta House in Kreuzberg.
Will you also be there?
Of course I will.
I think this is the reason to worth going there.
Yeah, I'll do one of the workshops, for example, and it's going to be much longer than this. And you can ask any questions you want. And I also do a talk at the main conference. And yeah, so I really hope to see you all there, of course, every single one of you.
Leonard, thank you very much.
You're welcome.
Let's have a short 5 minutes break to reset our brains, and we will jump into Kubernetes.
I feel the heat. Heat. I feel the heat. I feel the heat. I feel the heat. 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 I feel the heat. Heat. I feel the heat. You see the road I wanna follow. It takes a turn, it's hard to follow. I want your touch, I want your body. I feel the heat. Ooh, heat. I feel the heat. Heat. I feel the heat. Ooh, you see the road I wanna follow. It takes a turn, it's hard to follow. I want your touch, I want your body. I feel the heat. Ooh, it's you. It's you I want tonight. The heat is on. I want you here tonight. It's you. It's you I want tonight. The heat is on. I want you here tonight. I feel the heat. 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 You see the road I wanna follow. You take a turn, it's hard to follow. I want your touch, I want your body. I feel the heat. Oh, it's you. It's you I want tonight. The heat is on. I want you here tonight. It's you. It's you I want tonight. The heat is on. I want you here tonight. I feel the heat. It's you. It's you I want tonight. The heat is on. I want you here tonight. I feel the heat. It's you. It's you I want tonight. The heat is on. I want you here tonight. I feel the heat. Feel the heat. Feel the heat. Feel the heat. I feel the heat. Feel the heat. Feel the heat. Feel the heat. I feel the heat. Feel the heat. Feel the heat. Feel the heat. I feel the heat. Feel the heat. I want you here tonight. I feel the heat. It's you. It's you I want tonight. The heat is on. I want you here tonight. It's you. It's you I want tonight. The heat is on. I want you here tonight. I feel the heat. It's you. It's you I want tonight. The heat is on. I want you here tonight. It's you. It's you I want tonight. The heat is on. I want you here tonight. I feel the heat. Feel the heat. Feel the heat. Feel the heat. I feel the heat. Feel the heat. Feel the heat. Oh, I feel the heat. Feel the heat. Feel the heat. Feel the heat. I feel the heat. Feel the heat. Oh, I feel the heat. Feel the heat. Feel the heat. Feel the heat. I feel the heat. Feel the heat. Feel the heat. Oh, I feel the heat. Feel the heat. Feel the heat. Feel the heat. I feel the heat. Feel the heat. Oh, I want you here tonight. I feel the heat. Feel the heat. Feel the heat. Feel the heat. I feel the heat. Feel the heat. Feel the heat. Oh, I feel the heat. Feel the heat. Feel the heat. Feel the heat. I feel the heat. Feel the heat. Oh, it's you. Oh, it's you. Ooh, it's you. Ooh, it's you. I want you here tonight. 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 I feel the heat. 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 feel the heat, 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 feel the heat.
Okay, guys. Hello. Everybody who's in the drinking area, I use my magnetic skills to move you from this place to the audience. I promise it's worth, because the next speakers are really awesome. And then they bring with them a laptop full of interesting topics. Casey Cornatello,
Drello.
Calendrello,
Calendrello.
excuse me. I already trained a few times, but yeah, it's hard for me. And Sergiusz Ubaniak. This one is easy because he's from the same country as I do. So they will deliver a great show about Kubernetes. You can already see the topic, and yeah, the stage is yours. Let's rock and roll.
Thanks, everyone. Thanks, everyone, for coming. My name is Casey Calendrello. I work at CoreOS with my colleague, Sergiusz, who you'll be hearing from shortly. That's how I do that. Great. Sergiusz, who you'll be hearing from shortly. My name is Casey Calendrello. I work here at CoreOS, and this talk might also be called Kubernetes for Mere Mortals. I don't know, if by mere mortals you mean DigitalOcean users. So I'm going to make a very quick digression as a way to bring this all up, which is why CoreOS? CoreOS, we make an operating system. Our mission is to secure the world's internet, and by doing so, we hope to we have some pretty strong opinions about how you should be running your infrastructure. And a big assumption that we're asking you to make if you believe us is to use containers. So why containers, right? I know all of you are sick of hearing about containers, right? Like, yeah, me too. So let's just imagine you are a software developer, and you have code, you have lots of code. It does things, it might call some libraries, it's going to do some very wonderful and interesting things. It runs in an operating system. That operating system provides all sorts of wonderful, useful things like PID1. Thanks, Leonard. It's got a kernel, it's got SSH, it's got Docker, it's got Rocket, which I work on. But it also has your interpreter, it has Java, it has ImageMagick, and everybody uses ImageMagick, and it's awful. Yeah. So, like, where's the API boundary? It's here. Here's your app, here's the distro, and then everything else is your distro. And if you install your new application, you have to go bug your ops guy to install another version of ImageMagick. And then some other jerk comes and they need a different version of ImageMagick, and now you're totally in trouble. Or there's a software vulnerability, or there's updates, or there's all these changes. And so we think that the API contract is far too big in your operating, like in what is defined as what we call an operating system in this day and place of Linux. And so we think it should be here, right? So if we rewrite the contract and the operating system gets to be smaller, it gets to be dumber, it gets to be simpler. But the only way we can get away with this is like if all of this is user space. And so how do we deal that, right? Like all the tools that we use, like RPM or just tarzip, like that doesn't work in this world, right? So the answer, of course, is to use containers. We can run containers side by side. And these boxes are really strong. It's not just a packaging, it's also like an isolation format. But more importantly, everybody can have a different version of OpenSSL, which has a perfect API, and it can have a different version of ImageMagick, which has a perfect API. Because on the other side, these tools here, systemd, Rocket, Docker, what we are redefining as the operating system, we know that those have a really stable, really calm, stable interface. So what is that stable interface? That's CoreOS, right? So that's what we define the new world, the new century, the cloud operating system to be. It's a minimal distro for running containers. That's, in some sense, that's all it is, right? Containers are nice isolated bundles of user space code. Everything on the other side is not user space code, and you shouldn't have to worry about it because the API should be stable. So what's that code again? It's your container. It's your container, it's your interpreter, it's your libs, it's everything you need. But the cool thing about containers is they're also files. Files have a name, files have a hash, they can be content addressable, you can deploy them. We like files. We also like to sign files if any of you like security, because some people like security. So let's talk about you, the other you, the ops engineer. You've been totally sold on this container thing because you never want to run apt-get install on like an emergency ticket ever again. And you never want to find out that you broke an app because you installed another app. You want everything to be available, and you don't want to have to ever worry about this like sneaky user space because, yeah, it's the cloud, right? Like we've already fixed the hardware problem. Amazon solved the hardware problem, and now our containers are solving, and I don't have to do anything ever again. This is awesome, right? So I'm going to take my machine, and I'm going to go systemd run, and it's going to be great. And I'm going to give it half the machine, too. This is going to be awesome. Life is good. We have our container. We have our machine. Then, OK, great. Let's put some more containers in the world. And we put 2 on this machine. This is great. We are dividing up our machines. We add more containers, add more copies. And now they need to talk to each other. So that means you need to tell them about each other. So you just, I guess you could do that. That should probably work. This is, sometimes people call this a service-oriented architecture, or if their homepage is Hacker News, they call it microservices. You can call it what you want. So these things can really get quickly out of hand. I tried using the clone tool in Google Slides, but this is like, I got really frustrated after this many. And if I hate like drawing it, it's got to be impossible to manage. So what is our solution, right? Like, who is our savior in this world that's getting crazy and complicated? And the answer comes Google, and it gives us this. It gives us Kubernetes. Kubernetes is cluster-level container orchestration. That's 4 words. They're pretty deep. But maybe let's think about let's talk about what it does then. It does 4 big things. It does scheduling, which you can think of as deployment, but it's better to think of scheduling, and I'll talk about the why in a little bit later. It does service discovery, so that's the second problem we needed to solve of this tangled web of deployments and dependencies. It also handles the other messy parts of that world, so it does failure management. Containers die, nodes die, everything dies, everything is temporal. And the most interestingly, it also does scaling, so you can easily do scaling. You can easily scale up as you need more nodes and you need more containers. So the basic architecture of Kubernetes is pretty simple. There is a master controller or a scheduler which keeps all state in etcd. So the scheduler is actually stateless, which means that the scheduler controller is high availability. It can be easily replicated. You can use fairly simple tools to make more of them, which is because all of the state is kept in an etcd ring or hash. And then you have arbitrary number of worker nodes, all of which run a piece of software called the kubelet. So in Kubernetes, we like to start or end every single thing with the word kube. So there's hypercube, minikube, but the most important one here is the kubelet. Kubelet talks the container runtime on your operating system to run containers. It receives instructions from the scheduler. That's it. So the thing about Kubernetes that I think is really fascinating is that it doesn't really think about containers. It really thinks about the unit of scheduling is a pod. A pod is a group of 1 or more containers with a shared context. And this winds up being a really powerful abstraction for when you're actually trying to deploy real-world applications. And that shared context, for those of you who were paying attention before, is really just a namespace. So it's basically just one systemd nspawn call. So let's look at it. Let's get down and dirty. Let's look at a Kubernetes configuration file. It has some metadata, and I really want to highlight the important things right here, the labels, which are some identifiers that define this pod. We're going to come back to these a lot, so just pay attention to those. And it includes some containers, including information about how to find that container. So you can use a name, you can use the URL, you can use any other way that you want to describe a file, be it by hash, so the content addressable, or a URL, or anything like that. Kubernetes will allow you to deploy that file because it's just a file. It's just a package. And you can see here, this application right here consists of Redis, we'll say maybe we're using Redis as a cache, and Django, and as far as they know, they have their own machine, and it's wide, and it's deployed, and everything is nice and clean. So, but how do we tell Kubernetes that we want to actually run this code that we've given it? So we've got a container. We have defined how it's going to be installed. We say that I want Django, and I always want it to be run with Redis. But there's a lot more information we're going to need to provide, and that comes in a separate piece of information called a replica set. So you don't deploy on Kubernetes, you schedule on Kubernetes. To schedule, the way that you talk to the scheduler is through something called a replica set, or a replication controller if you have an older version of Kubernetes. So you give it a pod, and you ask Kubernetes to schedule it. But how did I give it a pod? I didn't give it the name of the pod. Instead, I actually gave it the selectors. And this is an important distinction to realize, that selectors or labels are really how we talk to the Kubernetes data store. Replica sets have their own properties as well, the simplest of which is count. But you can get it pretty arbitrarily complex. We have a customer who is scheduling, and one of the properties they have is whether or not the machine has an accessible GPU, because they're doing crazy trading stuff. But let's keep it simple for now, right? Anytime you change a property of a replica set, Kubernetes scheduler is going to recompute and reschedule, and you get your 5 pods now. So now I have 5 exact copies of my web application. Likewise, if a pod or node dies and we want it to have 2 copies, Kubernetes scheduler is always going to be running in the background, trying to make the real world look like the way you've declared it to be. So Kubernetes, of course, schedules you a nice new pod. So I have some applications. They're on machines. I don't know which machines they're on, and this is sort of a problem, because I don't actually have any idea how to talk to them. So in addition to configuring replica sets in Kubernetes, the other really important thing, the other data structure or data model that you want to be conceived of in the intro to Kubernetes is a service. They define how you're going to access. They're going to define how your pod is deployed to the rest of the cluster. And as an aside, I'm not going to talk about this today, but they're also who talks to your load balancer. So if you're using Elastic Load Balancer, or if you're using Nginx or HA Proxy, Kubernetes can configure that for you. And the best way to think about this is that pods are mortal, but services are forever. Pods can die, replica sets can die, but your service will always be alive. So this is sort of an example situation series. You can see the mapping between services and pods and why it isn't a one-to-one mapping. Services have selectors. They don't select replica sets, they select pods. And that's a really important disconnect. We want to be able to change your replica set, you want to be able to delete your replica set, you want to be able to alter your replica set. But all the service needs to know is how to reach the pods and how to make them available. This is a neat trick. You can have conditions as well. So you can see your beta will serve beta if it exists. Otherwise, just serve it to an available production pod. And just to get real, let's look at the actual. This is the actual YAML for sort of a semi-production or a real service. See, it has a selector. You're not selecting the replica set. You're selecting the app. And the important thing here is the thing I'm configuring in the service is the port. And also notice that there's a difference between the inside port, or sort of this is the pod level port, and the outside port, which would be the sort of the cluster level port. So how do you actually consume a service? This is one of the coolest things. I love networking. I love IP tables. I love all these things. And services in Kubernetes expose service IPs. These IPs, they're stable. They don't point to any pod. They connect. They're virtual IPs. They don't exist anywhere. And instead, this is one of my favorite things, is that they're actually per host IP tables DNAT. This is awesome, right? Because it's just contract. Contract is like what runs all of our internet connections. It's what's natting every single person checking Twitter right now. Contract is stable, it's fast, it's battle hardened, it's in the kernel. Contract is, if contract fails to scale, you are officially too big. So this is one of the most favorite parts of Kubernetes. I think it's deep, I think it's rich, and it's so simple, and it always works. Running on every single Kubernetes worker node, along with the kubelet, is a piece of software called proxy. And that's the piece of software that is going to be running. It is talking to etcd, it's getting information from the scheduler, and on each individual node, that's the one responsible for always for changing IP tables. And etcd convergence is super fast, so you almost never have to worry about gaps in your load balancing. Compared to, say, DNS-based load balancing, where you have timeouts of, a generous timeout would be 5 seconds, right? I'm sure if you've ever done something weird, you've seen DNS timeouts of a day, or applications. The favorite thing in the whole world is an application that resolves DNS exactly once and then never resolves it ever again, and your database goes down and it never talks to your new database. And so that's why stable IP is totally the way to go. Expose them via environment variables, or if you need to, you can expose them via DNS, and just let IP tables and let the node level kube proxy do all the work. So, sign me up. Have you guys seen, there's an amazing piece of software by Kelsey Hightower called Install Kubernetes the Hard Way. And he's not lying. It's really hard. And so my amazing colleague has got Sergiusz, which I'd like to introduce to you, has Kubernetes up and running on DigitalOcean in like 2 files. Sergiusz, take it away.
Second part of the talk.
Thank you.
Cool. Thanks, Casey. Really nice intro. Yeah, so how do I get started on DigitalOcean? I installed a few Kubernetes instances in my past, and I have a question to you. Who of you did install Kubernetes on DigitalOcean? On DigitalOcean, yeah, okay. So it's like 1. Oh, okay. Oh, 2 together. Okay, so there's like very few people. So how do we do it, actually? I mean, there are choices, many choices, actually. And as Casey indicated, there is one way of doing it, which is called Kubernetes the hard way, literally. Unfortunately, as you see, there's no DigitalOcean in here, so sorry. Then you have other possibilities. If you have ever lived in the code base of Kubernetes itself, there is an interesting kube-up shell script. And this guy looks pretty innocent, just 80 lines of code, until you go 1 directory up and you see like a whole bash framework. It's honestly, this is the biggest bash source code base I've ever seen in my life. And I guess the Kubernetes maintainers recognized that it's not the best idea to maintain a deployment story in bash, so they deprecated it. And then, I had a look at the blogs from DigitalOcean itself, and it's like 2 years ago. There is some Ansible playbooks about a year ago. So this is all nice, but not really like up to date. So I was in trouble because I thought I would prepare this talk like in half an hour and be done. But fortunately, I mean, Kubernetes recognized that the whole deployment story is kind of limited, and they are trying out to come up with innovative solutions. And there's quite some of them out there. One of them is Cargo, ADM. They're not quite there yet. And there is another one which I would like actually present to you. Is called Bootkube, which is a pretty interesting addition recently in a new space called the Kubernetes Incubator. And this is the thing that we are going to bootstrap a small Kubernetes cluster on DigitalOcean in a moment. And hopefully I won't fail miserably, because this is going to be a demo. But before we do it, what is actually Bootkube? The idea behind Bootkube is actually quite neat. Casey gave you a really nice introduction on how actually Kubernetes works with the replica sets, with service IPs, how you actually do deploy pods. And Kubernetes consists of quite some moving parts which have to be deployed. So why not use Kubernetes to install Kubernetes? Which sounds a little crazy, but actually it's not. It's essentially like the same metaphor you have with compilers. You need a compiler to compile a compiler. So why not piggyback on that idea and create something that bootstraps Kubernetes using itself? And sorry? Oh, sorry. You're right. It's a little small. And the only thing that you should need is to have the kubelet and a container runtime. And we, of course, prefer Rocket, to be honest. Why self-hosted? As I said, mainly for dogfooding the containerization model inside Kubernetes itself, and also use its own intrinsic features, to get the thing started. So I have already, because I didn't want to blame myself, a Kubernetes cluster installed, and you see I did it like 4 hours ago, using Bootkube. And what I mean with dogfooding Kubernetes with its own lifecycle features is that if we invoke this tool called kubectl, and we say get pods, then you see all the components of Kubernetes are deployed as first-class objects of Kubernetes itself. Mainly, the kubelet is deployed as a pod. The scheduler, which Casey talked about, is deployed as a pod. DNS, controller manager, the API server, scheduler, everything is deployed by itself. And you can actually also reach, for instance, the logs of a given pod using its own method. So we think this is very interesting, especially in the context of upgrading. Upgrading Kubernetes clusters usually is a pretty hard story. If you do it yourself and just manually deploy service files, it can be pretty hard. If you use intrinsic Kubernetes facilities, upgrading a Kubernetes cluster can be done using its own methods. Right? So you just apply the descriptors that Casey just showed you and deploy the Kubernetes components itself. So how does it actually work? As I said, there is a thing called Bootkube, which itself hosts a super little small Kubernetes cluster in process with all the components needed, except etcd. That one you still have to provide separately, and we will deploy it on DigitalOcean separately. And then this Bootkube thing includes the API server, the scheduler, controller manager, and all the components needed to actually launch pods. Then you launch a kubelet, which talks to this temporary scheduler, and which lives inside the Bootkube process, and then launches all the components that are needed on your real cluster. And then, as a second step, Bootkube just shuts off, and the real thing keeps on living and having its own life. And that's exactly what you just saw here on the slide before. So yeah, let's do it. I'm gonna delete the whole nice thing that I just showed you. That's probably a very terrible idea. So I think everything is gone. Of course, my terminal has a bug now. Okay, looks like we don't have any droplets. So first we will launch a etcd instance. And this is the cloud config. We are going to bootstrap the etcd instance using CoreOS itself. Pretty easy. We use a feature by etcd called the discovery service. And we just launch one instance of etcd. So my terminal works again. Okay. And then we can log into it, as you know, from DigitalOcean, hopefully. And then we see if etcd came up. Okay, something seems to be living. So we're using systemd live. Okay, so I just grabbed the IP address of etcd. And now what we are going to do, we are going to launch the Bootkube instance. I'm going to show you what is going on here. Okay, so again, a cloud config. The first thing that we do here, we bootstrap what we call Flannel, and Flannel is the middleware that creates the network fabric to have a pod network across many machines. So that's the configuration for this one. Then we have the actual kubelet, which we launch using the so-called kubelet wrapper, which is just nothing more than invoking Rocket, a special bash script using Rocket, which points to an API server, which initially is the Bootkube API server itself. And now you see we create another systemd service called the Bootkube render service. And this one does nothing more than just simply generate the metadata that is necessary to bootstrap your cluster. And you see we use Rocket, because we like containers, to launch Bootkube and render all the metadata files that are necessary for our new cluster. And once that thing is done, we start the actual Bootkube service. This is the temporary Kubernetes mini cluster, so to say. And you see there is a special type. It's called one shot for this service file. So we just invoke it, and once Bootkube exits, you know, the service is gone too. So let's log into the machine. Okay, what you see here is that Bootkube rendered all the assets that are necessary, exited. And now we have a little Bootkube running here that is just simply waiting until all the components are being deployed on the kubelet itself. Yeah, and here I invoke the journal control for the kubelet. We are downloading the container image for the kubelet itself, and now you see it is being started and is doing its thing. So I will just download the assets. Okay, and what you see here is that the parts are slowly being created, and hopefully at the end we will have a running master node, and we can simply add worker nodes. Yeah, and then you see already our master node is going out. Okay, my demo worked. I'm pretty happy. Questions so far? No, this is the Bootkube one. Once all the actual components will be up, you will see that this thing will exit, and then I have just to reissue again to get the actual API server. So we should just, yeah, you see now Bootkube shut off, and we should have, yeah, exactly. You see the connection was refused because the real API server is starting, and I'm just trying to, yeah, okay. And now the actual API server takes over, which is started by the kubelet, and the actual components come up. So this somehow worked, which makes me pretty happy. And now we can just simply add worker nodes using other cloud config. So this is pretty much it. If you are interested, I will submit all this shortly into the BootCube repository, and then you can get going on Kubernetes on DigitalOcean. I hope pretty fast. Okay. Yeah, it's running. Questions?
I have another one. How do you hand off from the temporary API to the permanent one on the kubelet? Like, how does the kubelet switch from registering itself with the temporary one?
Yeah. Internally, it's just simple file locking. So there is a file lock first being held by BootCube, and then released once it shuts off, and then the kubelet takes over. It's a very simple mechanism.
Okay.
Yeah.
Okay. Hi, thanks for the talk. So the question I now have is, we have Kubernetes up and running, but how do we expose services? So how is it actually like? Have we load balancers on DigitalOcean and all that stuff?
Yeah, that's a very good question. I didn't solve this here right now. I did some experiments using a nice project called Traffic, if you have ever heard about this, which is what internally Kubernetes calls a so-called ingress controller. And DigitalOcean, on the other hand, has a concept of floating IPs, which you can assign to master nodes of running Kubernetes. And this is not solved by BootCube itself. BootCube is just for bootstrapping purposes of Kubernetes. But if you want to have some notion of ingress controllers, I would say Traffic is the way to go. I think you will have to write still some code or some small Kubernetes controller to wrap it up together with the floating IP of DigitalOcean.
But it would run inside the Kubernetes cluster as well, like
yes.
Traffic inside Kubernetes?
Yes,
yeah.
Yes.
Okay, thanks.
Okay. The worker nodes are not up yet, but they should register themselves in a couple of minutes. Other questions?
Yeah. What do you do if the scheduler dies?
Sorry?
It's me here.
Who are you? Hands up? Ah, here, okay.
If the scheduler dies?
Right, so I just started one master instance. What you, of course, should do is you should bootstrap in a real production cluster multiple master instances. And then, sorry? Yes, the master actually is stateless. And then what you see here is that the API server has a so-called node selector, which Casey talked about, which will pick another master once one of them dies. I wanted to do a multi-master installation too, but that was just simply too short. But this is the way to go. And in the BootCube repo, you also have a multi-master installation sample there too.
Thank you.
Searching for question volunteers. Perfect.
No, just a little one. So that means that you're fully relying on etcd being up all the time?
Yes, exactly. So I installed only one etcd instance here. But usually you, of course, should install like 3 or 5 instances of etcd on DigitalOcean. I actually made the script in a way that you can install multiple instances of etcd. I just didn't do it because I wanted to have it done in the demo. Yeah.
I'm wondering if you could speak about the different backends that Flannel provides for the overlay network. If you have a recommendation, which one to use in DigitalOcean.
I can't speak so much about the backends. I was looking at Casey if you have more information. The only interesting thing right now that is going on in the scene is that there is another project called Calico, which does the network fabric on TCP layer 3. And the two projects actually join together. Yes, exactly. And it's called Canal. So you can expect some news from that side.
Okay, thank you.
Yep.
Okay, I think that's it. Great, big applause, Sergiusz. And Casey.
Oh, right.
We need the random generator. Is there anybody who didn't pick up a number? Too late? Okay.
Okay, come over. Get the mic.
Okay, so we
Okay.
have this lovely command here. So the way this is going to work... Oh, sorry. Okay, the way this is going to work, we're going to do... we have 2 tickets to give away, so we're going to do this twice. And so there are still some numbers here, so we might not have an exact number, but if you're the closest, and if there's 2 people between it, then we'll just give it to those 2 people. Okay? So let's figure out what we have. 44. Anybody have 44? Anybody have 44? Or maybe we should just do it until we get an exact hit, right? That would make more sense, yeah. Okay. Can we do another one? 99. Anybody have 99? Sorry. Yeah. 40. B40. Oh, we have a 40. Okay, good. Okay, contact me afterwards and I'll get your email address and I'll assign a ticket to you. Okay, the next one. 45. Anybody have 45? Oh, his neighbor. Okay, good. Okay, so we have 2 winners. So great. And anybody who has not won, which is the rest of you, you can still come. It takes place on Wednesday. Yeah, among others, we have Leonard talking about the journal. That's one of the workshops. So we also have David Strauss from Pantheon, which is I think who you were referencing was talking about the running applications really dense using the socket activation. He's going to be talking about building applications to use a systemd. And yeah, then we have I think one about nspawn, and yeah, and then also one about a general I think using unit files called I think demystifying systemd. Okay, yeah. So that's next week. Hope to see you there, and get in touch with me. I'll get your email addresses and assign you tickets. Thanks.
Okay, one more time, thank you for being here. Feel free to stay a little bit longer, chat around, network a little bit, and most importantly, share some knowledge. Thank you very much.